In this video, we're going to bring together several aspects of our discussions of stereoisomerism and really spend some time thinking about how the stereochemical relationships between isomers relates to their properties, such as melting point, and then new properties like optical rotation, and we'll revisit the idea of biological activity. We will look at something called optical activity. We will think about a process called resolution. And finally, and probably in a separate video, I will show you how to use Fisher projections to represent stereoisomers. And then finally, we've been thinking about this statement, life is chiral, but by the end of this video, hopefully you can really think deeply about this idea. So let's get started. Now we're going to review enantiomers have the same properties except how they interact with other chiral substances. So for example, they have the same melting point, they have the same boiling point, they have the same solubility, they would have the same color. Melting point, boiling point, solubility, anything else you can think of here. However, they will have some different properties. These different properties will involve interacting with other chiral substances. So there can be different chemical reactivity with chiral substances, such as they can have different smells because the proteins in your nose are chiral. They can have different tastes because the proteins in your mouth are chiral. And then there can be different chemical reactivity with chiral molecules, more generally. Okay, now diastereomers, however, they are different. Diastereomers, different. They could have different everythings. They could have same everythings. It really sort of is on a case-by-case basis, but they could have all different properties. Diastereomers are different. And then finally, constitutional isomers are different as well, and I have this in parentheses since it's not a stereochemical relationship. All right, keeping those principles in mind, how might you separate a mixture of these isomers in lab? Well, perhaps the first thing that you should do is think about the relationship between these two molecules. And these two molecules are enantiomers of one another. I have identified their stereocenter, and you can pause and figure out which enantiomer is which here. So convince yourself that the molecule on the left is the R enantiomer and the molecule on the right is the S enantiomer of this molecule. Let's think about how we would separate a mixture of these molecules in lab. So think about the typical methods of separating mixtures. Well, there's filtration, there's distillation, there's chromatography, crystallization. And let's think about what all of these techniques exploit. Well, filtration, you would need to have different phases. Are two enantiomers going to have different phases? No, they have the same physical properties. For distillation, you use boiling point, different boiling points. Will these two molecules have different boiling points? No, enantiomers have the same boiling point. Chromatography, it exploits differences in polarity. Polarity is a physical property, and these molecules will have the same polarity. And then finally, crystallization. This exploits solubility. Well, these two molecules will have the same solubility. So basically, if we are going to separate a mixture of these, we are going to need something chiral to do that. Just recall the handshake. We need something chiral. We need one hand to distinguish between these two hands of this molecule. Okay, so what that process is called resolution. So resolution allows you to separate a mixture of enantiomers. So here you start with a racemate. A racemate means it's a 50-50 mixture of two enantiomers. So you have your left hand and your right hand, and they're in equal mixture, or equal amounts. Now, enantiomers have the same physical properties. So currently, we cannot separate them with any of the techniques that we have learned in labs so far. However, if we could magically mix this racemate with something, we'll call it X, and turn them into diastereomers, then we would be in great shape because diastereomers have different physical properties. So that would be excellent. And then we could separate the mixture by one of these techniques that I've listed here. And then once you had the two diastereomers, you could somehow magically remove them from X, separate them back, and get the two enantiomers. I actually haven't mentioned plus and minus to you yet. I'll explain that in a little bit. But those are just the two enantiomers. So you can pretend it says R and S. So let's go ahead and look at an example of resolution. So these are the two right here. These are the two molecules I had on the previous slide. We've just abbreviated the ring here. This can be abbreviated as pH, which means phenyl. So that's what you see up here. So we have our racemate. Again, a racemate is a 50-50 mixture of enantiomers. We have our R and our S. Now, it turns out that some molecules, as we've discussed, exist in nature as single enantiomers. So this is 2R, 3R tartaric acid, and I'll tell you what the plus means later. And it exists in nature as a single enantiomer. You can buy it in its enantiomerically pure form at the chemical store. Yay! Or, you can find it in wine and other natural products as a single enantiomer. So this would be, a left hand. This is your neighbor's left hand. And you're mixing it in with your left hand and your right hand. And so you're going to have a normal handshake and you're going to have an awkward handshake, like we saw in a previous video. Okay, so we're going to mix them together. Now, what's really important here is that this molecule that we are thinking about resolving, it's an amine, and amines are basic. Tartaric acid is an acid. You can see this carboxylic acid functionality here, and so they undergo a proton transfer reaction. So proton transfer reaction. And you can see they make salts. So you've gone from NH2 to NH3, and you've deprotonated the tartaric acid. So now you have the carboxylate instead of the carboxylic acid, and then opposites attract. Now at this point, you've made diastereomeric salts. I'm going to zoom in a little bit. So these two salts here, these are diastereomers. Well, how do I know that? Well, just look at the configurations. So we have R, that's the stereocenter on the molecule we started with, the alpha phenylethylamine. And then our stereocenters for the tartaric acid are R and R. So we have R, 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 the pirate stereoisomer. And then over here on the right, we have S, that's the stereocenter at the alpha phenethylamine that we're trying to resolve. And then R and R. So as you know, when you switch one stereocenter, but not all, so we have R to S, but these two R's stay the same, that makes diastereomers. So you've switched some, but not all stereocenters. So yes, we have diastereomeric salts. So now it turns out these diastereomers, they have different properties. One of these salts is soluble. The other is insoluble. So what you can do is you can filter them. We can maybe draw a picture of that. So over at this phase here in the diagram, we would have in solution. So we'd have a solid, and then we'd have in solution in the mother liquor. So we'd have in solution, we'd have the RRR, it's still dissolved, and then the solid, this would be the SRR. So it's going to be a solid. We're going to filter them, And then super, we're not going to worry about a beautiful picture here, but super, that means in our filter paper, we're going to have the SRR. Down here in the mother liquor, we have the RRR. So then, of course, we've separated the enantiomers, and that is really, really awesome because it was impossible to do by any other way until we turned them into diastereomeric salts. So now we have our two enantiomers, but of course, they're still with the tartaric acid here, the tartrate. So how do you get rid of it? Well, you simply just treat them with base. That will deprotonate the ammonium and turn it back into an amine. Neutral organic compounds are insoluble in water, as you know. So then you can just do another filtration to get, for example, the R enantiomer away from the tartrate because that will just stay in water. So you would do another filtration. All right, so that's where we said convert. That's just that add base, and then you can do another filtration and you would get your enantiomers away from this magical compound X, which in this case was tartrate. All right, so that's a resolution. You take two enantiomers, you mix them with something chiral, you make two diastereomers, lots of writing on this slide, and then those two diastereomers have different properties, and you exploit those properties, and then hopefully at the end you can get rid of whatever you mixed it with initially to get back your pure enantiomer in a vial. So keep in mind, right, this was the demonstration. Although enantiomers have the same physical properties, including solubility and others, diastereomers have different properties. And so we could exploit that relationship, that difference in properties once we made diastereomers. So enantiomers may have the same properties, but then when we made diastereomers through this resolution process, they were different and they had different solubilities, and we could separate the two enantiomers from one another. So let's take another look at a demonstration of enantiomers interacting differently with chiral things. So for the resolution, the chiral thing was tartaric acid. This time, the chiral thing is a little more difficult to wrap your head around, but we're going to be able to do it. So we're going to think about how enantiomers interact with plain polarized light. So let's go ahead and think about that now. So if we just have light in the room around us, light is a wave. That wave can be aligned in all different directions. So if I take a slice of light in the room, it's going to be aligned in all different directions. Okay. Now I could take that light and I could run it through a filter. In other words, what's called a polarizer. And if you have polarized sunglasses, you have a polarizer at home. Look at your cell phone with your polarized sunglasses on. It should look funny because it's filtering out some of those wavelengths or some of the light that's oriented in different planes. And you're just going to be seeing light that's oriented in a single plane. Okay, so now we have what's called plane polarized light. Now I know this is weird. In the previous example, that chiral thing we were interacting with our enantiomers was tartaric acid, but in this example, it's plane polarized light. Plane polarized light will act like a chiral substance. So it acts like a single hand that you're going to subject your enantiomers to. Now it turns out that solutions of enantiomers can rotate this plane polarized light. So let me show you. I think I'll just show you up here at the top. So I could take this plane polarized light and I could put it through a solution of some chiral substance. So let's try S-butane 2-ol that we've been talking about quite a bit in our videos. So this is a chiral substance. Let's say we have an enantiomerically pure solution of this substance. when I send that light through our sample here of S2-butanol, that light will come out. But what's interesting is that the light is going to be rotated. It's going to be rotated. Let's say it was initially straight up and down. It's been rotated now by some angle. Okay, so the light has been rotated by some angle. And this angle with which by which the enantiomer has rotated the light is called its optical rotation. So the enantiomer has an optical rotation, an angle by which it will rotate plane polarized light. Now, if the plane of the light rotates clockwise, as it did in this case for S2-butanol, the compound is referred to as dextrorotatory. And in fact, for S-butane-2-ol, the S enantiomer is the plus enantiomer. So remember, you heard that word plus, or that term plus before. We didn't know what it meant. And it turns out that its specific rotation, pure S-butane-2-ol, will rotate plane polarized light by 12 degrees. So the positive also refers to clockwise. Now, if the plane of light rotates counterclockwise, the compound is called levorotatory, and that would be the minus enantiomer. Okay, so a couple of things here. Let's tackle R2-butanol first. So here is R-butane-2-ol. If S-butane-2-ol has an optical rotation of positive 12 degrees, R2-butane-2-ol will have an optical rotation of minus 12 degrees. The two enantiomers have the same magnitude, so a 12-degree rotation of plane polarized light, but with an opposite directions. So the two enantiomers rotate plane polarized light, which is acting like a chiral substance, in opposite directions, but with equal magnitude. Okay. So that's the first thing to keep in mind here. And then the second thing is this plus or minus, so the direction in which the enantiomer rotates plane polarized light. These are physical properties. And so in this example, S2-butanol was the plus enantiomer, but that will not always be the case. S will not always be the plus enantiomer. It's really going to depend. So plus and minus are physical properties, and you cannot predict them based on R and S. Unless, of course, you know that one enantiomer, the S enantiomer, is plus, then in that case, you know the R is minus. But if you don't know that, you cannot just guess it based on R and S. Now, there's a standard form for reporting optical rotation data. So you say alpha, that's the optical rotation. It's gathered at some temperature. So this would be the temperature. And then typically you also tell what kind of light was used. So usually it's D, and D is telling you what type of light. In this case, it's light that's coming from the D line of sodium. So that's referring to one of the electronic transitions of sodium that emits a certain frequency of light. Sorry, I lost my words. And then you would say what that was equal to. So positive 19.2 degrees, for example. Of course, I'm making this number up, okay? All right, so let's think about what would be the optical rotation for a racemic mixture of a chiral substance. So if you have a racemic mixture, you have 50-50 of the plus and the minus enantiomer, whatever configuration that they might, plus and minus might be. So the plus enantiomer, it's going to rotate plane polarized light in one direction. And remember what we learned up here, the other enantiomer, it's going to rotate it in the opposite direction with an equal magnitude. So what will be the net optical rotation for a racemic mixture? Well, it will be 0 because one enantiomer will cancel out the effect of the other enantiomer. Let's rotate the light back. It's also important to mention here that achiral substances, they don't interact with plane polarized light in any meaningful way, so they're also going to show an optical rotation of 0. Now, why is any of this useful? It's kind of interesting, maybe to some of us, but why is this useful? Well, let me show you. So what you can do is you can measure optical rotations in lab, and you could actually calculate the amount of an enantiomer if you had some mixture of enantiomers that wasn't 50-50. Let's say it was enantio-enriched. It had more of one enantiomer than another. So let's take an example. Let's say that the pure plus enantiomer of some substance, so we'll just call it substance, has an optical rotation in the literature of 24 degrees, positive 24 degrees. So let's say in lab and experimentally you've tried to make some, or you've maybe isolated from nature, you've isolated this substance, and you find that the substance in lab has an optical rotation of 19.2 degrees. What you would do is you would take the observed optical rotation and take the ratio with the literature optical rotation. So we would get 19.2, that's our observed rotation, divided by 24 degrees, our literature rotation, times 100. And this gives you 80%. 80% is referred to as the enantiomeric excess, or for short, it's called EE. And this means, so EE, or enantiomeric excess, it's the percentage of the major enantiomer minus the percentage of the minor enantiomer. So for this example, 80%, that's equal to 90 minus 10. So this fictional mixture that I had measured in lab, it contained 90% of the plus enantiomer and 10% of the minus enantiomer. And if you're wondering where I'm getting that from, well, I picked an example I could do in my head, but it's a 2-equation problem. So the EE is the percentage of the major isomer minus the minor isomer, and then of course 100 equals the percentage of the major plus the percentage of the minor. So it's just a 2-equation math problem that I picked easy numbers to do in my head. So let's make sure we get the point here. Why do enantiomers interact differently with plane polarized light? You've got it, because plane polarized light is basically a chiral object. Okay. What types of substances will be optically active, meaning that they will rotate plane polarized light with some net effect that you can observe? Well, chiral substances where you have more than one enantiomer, more of one enantiomer than the other. Otherwise, they cancel each other out, right? All right, and then finally, what types of substances will be optically inactive, meaning they will not show any rotation of plane polarized light? There are 2 answers. So the first one is achiral substances, and the second is racemic mixtures, where you have both enantiomers. They will rotate plane polarized light with equal magnitude in opposite directions, so they cancel out the effects of one another. Okay, let's move on. See if we can bring it all together here. So I have 4 molecules drawn for you on this slide, and I want you to consider the relationships between these molecules. Circle all stereocenters, assign RS configuration, and label isomeric relationships. So enantiomers, diastereomer, conformational isomer, whatever you think the relationships are. Please pause and do that. It's very important. This is what the pause button looks like. All right, pause. Welcome back. This is what you should have. We have a molecule with two stereocenters. They're circled in red. And we know that the number of stereoisomers is 2 to the n, where n equals the number of stereocenters. So we have 2 stereocenters. And of course, we have to account for meso compounds, or mesoisomers. But of course, the 4 groups on these 2 stereocenters are vastly different. So we don't have to worry about that here. So there are 4 stereoisomers for these molecules, this molecule. And we have them drawn here. 2 sets of enantiomers and then several sets of diastereomers. Okay, now, so you have all of that figured out, the relationships. You have them on this slide. And I have given you here some physical properties, and I would like for you to fill in the rest of this chart based on what you know about the relationships between the properties of enantiomers and diastereomers. Okay, I have the relevant data filled in here. Is it the same as what you thought, or is it different? So can we summarize the effect of stereoisomeric relationships on physical properties? Yes, we can. So for enantiomers, what do we see for optical rotation? Well, we see that 2 enantiomers have the same magnitude of optical rotation, but opposite signs. One rotates it counterclockwise and the other clockwise, as highlighted here with these 2 enantiomers, the SS and the RR. Okay, what can we say about diastereomers? Well, we've already been saying this. Diastereomers are different. And they have different optical rotations in a way that, you can't really predict. This set of diastereomers has different magnitude and sign, but we have this set of diastereomers. They have the same sign, but different magnitude. They're different. That's the bottom line. So diastereomers are different. Okay, what about melting points? Well, of course, the enantiomers have the same melting point. And diastereomers, different. They're different. Diastereomers are different. Okay, so let's take a look at these 2 molecules. I want you to analyze them. What is the relationship? If there's any stereogenic centers, assign those stereogenic centers. Go ahead and pause and do that now. Okay, these molecules are enantiomers. They have 1 stereocenter, and that stereocenter has different configurations in each molecule, and that makes them enantiomers. They are non-superimposable mirror image isomers. Of course, they're not drawn here as mirror images, but you can see that they have the same stereocenter, they have the same connectivity of atoms. They only differ in how the atoms are arranged about the stereocenter that's indicated with the purple star. Now, what's the big deal here? Well, it turns out that this is a drug. Its name is thalidomide, although it goes by a different name now. So it was called thalidomide in the 1950s, and this was a drug that was used to treat morning sickness. Because the R enantiomer is an antiemetic. That's a fancy name for it helps you with nausea. And so pregnant women, for example, they might feel nausea. And so this was given to pregnant women to help them with their nausea. Now, unfortunately, the S enantiomer, this causes limb bud apoptosis. What? Yes, we're all biologists. Apoptosis means cells die. Limb bud, that is a growing limb. What has growing limbs? Fetuses. Who's taking antiemetics? Pregnant women. So tens of thousands of babies were born in Europe with arms and legs that had not developed because their mothers had taken this drug and they were told that it was okay to take this drug. Actually, in the US, the FDA had not approved it, and so it was not taken in the US. But in Europe in the 1950s, this was given to pregnant women because it, one enantiomer, relieved nausea. The other, unfortunately, was teratogenic, and it caused birth defects in the developing children. So I have something to tell you, though. This is actually still a drug today, but it doesn't go by the same name. So this is still a drug today, and it's because it's active against multiple myeloma cells. So this is a treatment for multiple myeloma. But of course, they don't give it to pregnant women because, we know the deal, right? Now you would say, well, why would anyone be given a drug that's 2 enantiomers? Well, because when you make the molecule in lab, remember, these have the same exact energy. They have the same exact everything about except how they interact with other chiral substances. So you make them both unless you do something fancy, unless you use some sort of chiral reagent or you would do some resolution. And it's even more complicated with thalidomide because even if you make one enantiomer, turns out they interconvert in your body. But let's kind of stay to the point here. The point is, this drug was given to people as both hands, the left hand and the right hand. And you can see it had very different biological activity. So why is that? Well, you all know why. Because life is chiral, right? And life is chiral because the building blocks of your body, for example, amino acids, exist in nature as a single hand. And this is fascinating, and I've posted a paper that you can look at if you would like to think more deeply about this. But amino acids exist in nature as a single enantiomer. So this here is an L amino acid, and all the amino acids that you find are L amino acids. Let's take a look, assign the stereochemistry of the stereocenter. So we would have nitrogen as 1, this carbon is 2, R would be 3, and hydrogen's going back. So 1, 2, 3, that's S. So amino acids exist in nature as just the S enantiomers, which again is totally crazy. Why isn't there the R enantiomer? Well, there isn't. And so that means that you have a single enantiomer of proteins. And so those single enantiomer of proteins are like a left-handed glove, right? And a left-handed glove would interact differently with a left hand, which would fit it, and a right hand. And so it can be more serious than like a normal handshake and an awkward handshake. Your awkward handshake can become limb bud apoptosis. So life is chiral, and that's partially why we're discussing this topic at all, the properties of enantiomers and other stereoisomers. Okay. And in fact, as we think back, and this is a slide that you've seen before, we think back to the molecules of life, these are all chiral. And partially because, 3 of these are sugars. So we have glucose. Glucose has those 4 stereocenters. You have glucose twice here. And the cyclic form, it actually has a 5th. Look at the nucleotide. This has stereocenters as well because of the sugar backbone, estradiol, stereocenters, and all of these molecules exist in your body as a single enantiomer. So when these nucleic acids make RNA and DNA, they are single enantiomers. So life is chiral. Your body's just a left-handed glove. And when you put 2 different hands in it, you're going to get two different reactions. You're going to get the normal handshake and you're going to get the awkward handshake, possibly. Not definitely, but possibly. So we have to consider this when we think about how chiral substances can interact with the body. So I think that this is a pretty good stopping place for this video. I'm going to pick up with our last learning goal in a separate video. But now we've really thought deeply in this video about how stereoisomeric relationships can affect the properties of molecules, such as their melting points and other physical properties, their optical rotations, and biological reactivity. And hopefully everybody can explain this statement, life is chiral, and then they can describe to me why it matters. Time to practice.